Today I'm going to talk about this paper TED, which refers to teaching explanations for decisions. This is published by IBM in one of the ethics and reasoning conferences. And they have a follow-up paper to this one, which I'll briefly touch on, which is teaching AI to explain its decisions using embeddings and multitask learning. And the idea presented in the paper is very simple, but we thought was quite useful with regards to what we're working currently with explainable AI. So the idea is to provide meaningful explanations, and they are specifically mentioning that they want to match a mental model of a consumer. And the way to match this is to get these explanations from experts in a way you would annotate a training data set. We'll have a small use case later in the paper which make things more clear. So yeah, they reiterate that the automated decision-making system should provide meaningful information on the logic used to reach a decision. And the way they interpret meaningful information or explanation, they say that there should be three properties to it. It should be understandable by any target audience, and it should be actionable, and it should be flexible enough to support various technical approaches. So, and what they say is that these post hoc methods are not the best way to do this, or how we have a deep learning model and we create a post hoc explainer is not exactly, or trying to explain the inner workings of a machine learning algorithm is not exactly the way to get meaningful information to present as explanations. So I go down. So what they propose is a model that jointly produce both decision as well as the explanation. And in their paper, they present this framework called TED. It's kind of a very simple idea that can be instantiated in many different forms. They present another form in their other paper, which we'll go into detail later. And they discuss some results as well. Just to be clear, their evaluations don't really explore the depths of machine learning problems and explanation challenges we have seen in literature, but I think it's a start and it's about getting there. So at the beginning of their paper, they explore explanations and what are the challenges and what are the target audiences. I thought it'll be interesting to go through them, although it's kind of disconnect from the rest of the paper. They also present their own view of explanations, and they had a very good analogy, which how they weave explanations, which they say as communication from person to another person. Should provide like a justification as to why they made a decision, and they find this analogous to mathematicians providing a formal proof. And they go on to explain that when it's non-mathematical, providing this proof is very subjective, and also it is very challenging, similar to how they use non-expert jurors in the legal system to provide the intuition and experience when making an argument and then finally a decision. So what they're saying is, if human-to-human explanation, if this is so difficult, we have the same challenges when we have system-to-human explanations, or like a deep learning model to human explanations. They formalize three characteristics. First is justification, and explanation should have the justification for the decision that they're trying to explain in order to increase trust on the decision. And then the complexity of the explanation needs to match the complexity that is capable of understanding by the consumer or the target audience. And thirdly, domain match. These explanations should be provided in a way where they are reusing the terms of the domain. So again, it is part of the, I feel like it's part of the complexity matching, where the user is presented with an explanation with familiar terms of the domain. Then they discuss 4 different distinct groups of people we would provide explanations to. The first being end user decision makers. So they make a distinction about the end users who make the decisions, and as well as end users who are affected by the decisions, which this is something I saw different from other papers where we usually treat them as a single group of end users. So the decision-making end users are people like physicians or loan officers, whereas affected users are like patients and loan applicants. So they make that distinction, which is kind of neat. And then we have the regular, the other groups we've seen in other papers, regulatory bodies or third-party interest groups, and also AI system builders who are interested in the inner workings of the AI model. And so what they highlight is that these explanations, there are different types of consumers and it's subjective to the circumstances. So they kind of rephrase this justification, complexity match, and domain match, saying they have different needs with different level of sophistication and different levels of domain knowledge that we need to match when we are providing a useful explanation. What I wanted to highlight is that their breakdown of characteristics and uses, they kind of refer to other papers, but it's kind of different from what we have seen in survey papers earlier. And I'm going to skip the related work. I didn't feel like it's very critical or like extensive. It's something we haven't seen before. So I'll jump on to the explanation, the framework, the TED approach, as they say. And they begin with a use case where they try to explain their intuition. So they refer to this loan approval officer training a new loan approval officer. So it's there's a supervisor and there's a new employee. What the supervisor will do to train this new employee is go through some sample cases and explain to the new officer why they reach a decision. So if we take a case, these were the attributes led to this decision and why they rejected or accepted this case. So they would say something like it had insufficient salary, or some form of reasoning that the superior will teach to the new loan officer. And thereafter, the new loan officer, after their training period, they're going to reuse these reasonings, the learnings, and carry on, like work as a regular employee on their own. So they find this is analogous to how we do supervised learning. What they want to do is the explanations are taught into a decision model, and then the learnings are reused afterwards. So ask the training dataset to teach us not only how to get the correct answer, approve or reject, which is the decision, but also provide the correct explanation, such as insufficient salary, too much existing debt, or insufficient job stability, things like that. For in this case, looking at this idea, so yes, the training data need to be annotated with the reasoning behind the decision for each of the data instance, which is discussed later how it can be feasible or infeasible if there are ways to overcome the challenges with that. So then going into the formalization of their method, they introduce the set of features, the labels, and the explanation. So in this case, yes, we are modeling it as a supervised learning algorithm. But in this case, we have the data, which or the data instances, the features X, the label Y, which the things we are familiar with. But also it has a third component, which is an explanation. For each data instance and its label, there's an explanation which can take any form. It's a bit of a stretch to say it can take any form, but let's go with it for now. So for example, for loan approval, they will have the set of attributes of the loan application, and then the decision that was made and the reasoning behind that decision. So they present an instantiation using simple Cartesian product, which refers to, so if you have set of labels or set of Y's and set of E's, what they do is they treat each Y-E pair as a label on its own. So once you learn a model, the model will predict Y-E instead of just Y or just E. What you only have to do is once you have Y and E, you just have to break them down, which they explain in this diagram. If I go in detail, so in training time, in our training data set, we have X and Y, but not only X and Y, we have an explanation as well. So they introduced this dotted line component, which is a merge between Y and E. In their instantiation of this paper, it's a Cartesian product. This does increase the number of classes, as you can imagine. Again, we'll talk about that later. So we have, when it's Cartesian product, we have a set of YE class labels. Then our data set become a standard supervised learning training data set where the input is X and the label we are trying to predict is YE. Then we can put this through any standard multi-class classification algorithm to learn to predict YE. And the loss functions, those things stay the same because it's again modeled as a multi-class classification function. And then at the end of the training, we have a model that can predict YE given X input data. So once we have a new X instance or say loan application, we can use the model to predict the YE. So the output is not just Y, but E as well. Then they introduce this component in the dotted lines, which decomposes. So they introduce two components to merge and then to decompose the Y to a YE, the YE to a Y and E separately, which gives you the prediction and also the explanation. The important thing to note here is that these explanations are predefined, whereas in a post hoc system, we are used to saying very custom or very a variety of explanations depending on the data instance. But in this case, we kind of know the set of explanations we expect from the model, which is something that's highlighted in other like in reviews as well, where can you be consistent with an explanation? If you give a data instance as the input, would you get the same explanation in different tries? So in this case, yes, it is made sure because you are predicting it as a like a categorical classification task. So that's more or less the essence of the paper. The approach is quite simple, but yeah, when we try to implement it, when the E is more complex than just a set of explanations, it can get complicated. And I think they're yet to explore these complications, but we can see what they have done. So they have an example on how to do this Cartesian product instantiation of the TED framework. So they're referring to this recommending cancer treatments use case where PI is a patient and TJ refers to a treatment. So the training data set is simple, where you have a patient, the attributes, and the treatment that was predicted, decided for them. And what the addition that the TED approach would add is the explanations. So for each patient treatment pair, there's an explanation. As you can see, there are treatment A is recommended for 4 people, treatment B for 3, and treatment C for 1. And here we can see now that they've been annotated by an expert to provide explanations. Treatment A, 2 persons who were given treatment A get the explanation 1, and the other 2 gets the explanation 2. So it doesn't have to be the same explanation for the same when it's the same label, but annotated by an expert looking at their data. Again, there's another explanation for some of the people who got treatment B, and there's another person who got treatment B and got a different explanation, and also there's a different explanation for treatment C. As you can see, in a real world situation, the Cartesian product doesn't always hold. You don't have to have training data for, you don't have training data for all the possible combinations of the Cartesian product. So you might, there is a challenge of ending up with data instances where you don't have data instances for all the possible combinations. So that could affect learning of the model, which I don't think they've discussed in the paper. So what we have at the end of annotating is this triplets, let's say, where you have a patient, their label, and their explanation. What they mean by the Cartesian product is just you put together the label and the explanation so that the learning model will predict the label and the explanation, which you can then use that decomposing model to break down into a decision and a explanation. They have a visualization of how this classes become a different class distribution once we apply the Cartesian product. So first, before annotating with explanations, we had 4 instances for class A, 3 instances for class B, and then 1 for class C. Once they are once the Cartesian product is applied, there are 5 classes instead of 3, and 2 for 3 classes, 1 for the rest of the 2 other classes. And the idea is simple. Now that we again have a pair of input and output, you train the classification algorithm of your choice, and then break down and get the classification and the output. Before going into evaluation of this method, they talk about several advantages they see in this approach, which I think we will go into a bit of discussion later on or now. So they list several advantages, which is quite forthcoming before giving us any evidence that it actually works. So they talk about how they can ensure complexity and domain mesh. They say they guarantee to match the complexity of the mental model of the domain because these explanations are created by a domain expert. I think it can be argued that a domain expert who provides this explanation is generally for the cancer treatment case, it can be a physician, but it's quite a stretch to decide that it does the domain match for a patient. So yeah, there are some arguments they make that can be argued later for us. So again, dealing with incomprehensible features, they say that the explanation format can be any type. They are not limited to being a function of the input features. Again, can be a bit of a stretch in practice. And the next one is accuracy. They say the explanation will be accurate if the training data explanations are accurate. So this is kind of, please jump in. I thought it's kind of funny because we know it's a supervised learning classifier. Unless you get 100% accuracy on your test data, this is not a correct argument to make, even before you show your results. So yeah, there are some argumentative things. So generality. It says the approach is independent of the machine learning classification algorithm, that it can work for any supervised classification algorithms. Again, I think it's true when it's very simple explanation types, when you can put them through a Cartesian product, make it a label, and make it reusable set of explanations that are pre-existing. But there can be instances where any machine learning, any supervised learning algorithm is not the preferred method. Well, there are some good points they make about preserving intellectual property, that the fact that they're not trying to expose any details of the machine learning algorithm, which is actually correct. We are not trying to explain the inner workings of the machine learning algorithm that can lead to leaking important intellectual properties or learning of the machine learning model or any training data. But in this case, it's protected. Easy to incorporate. They claim the Cartesian product approach does not require change to the current machine learning algorithm. I don't 100% agree here as well. It's not easy to incorporate a new explanation because you have to change the output of the supervised learning algorithm. Basically, change the output is quite, the supervised learning algorithms, the main feature is that you have a fixed set of outputs. So if you train a model where you have 2 outputs and 3 explanations, you end up with 6 outputs, but it's fixed after you learn the learning model. So yeah, I don't think it's as flexible as they claim it to be. The 3 other ones, educates consumer. Yeah, I would agree. Process of providing good training explanations will help properly set expectations of what kind of explanations the system realistically provide, because they have to do this exercise where they go and annotate the training data, even if it's not the whole data set. They go do this exercise where they actually sit down and look at the data and look at the label and try to come up with an explanation for the training data, which can be a good exercise to understand the biases of the data they find and how their decision. It can be a debugging task on its own when they look at this, when they do this exercise of annotation, which they also talk here may reduce bias of the training data, because they look at the data in more detail than we would do in other post hoc approaches, where we just take the model that's already built, that may include biases already, and then try to explain. Here, you are involved in the explanation process before creating the model itself, which can be a really good approach. Improved auditability, yeah, again, the domain experts will have enumerated all possible explanations. So yeah, the strictness of the supervised learning output layer makes them be very comprehensive. when they explore what are the possible explanations, what are how they match with the decisions that are made looking at the data. So if they do it properly, the process of labeling can introduce these desirable features like educating the consumer and improving readability and reducing bias.
Angie,
Yeah.
I think to raise hands, I have a very quick comment about the bias point. Do you think that by adding the Cartesian product, it increases the number of classes, but the same number of training data, which makes it more likely to be overfitting as well?
Yeah, exactly. Like there are classes where you don't have enough data, and there can be classes where you don't have any data at all, because this Cartesian product captures all the classes instead of what classes naturally occur.
Yeah.
Yeah, there is that's something they have not discussed, because when we look at a supervised learning algorithm, these are the challenges like imbalanced data, the challenges they've been working on. But this approach kind of introduced those problems again back to the supervised
Yeah.
learning
Yeah.
approach. Yeah, definitely.
I see Kyle has a hand raised.
Yeah, it was
Kyle?
just more to follow up some of Angie's comments on these advantages. I think that this is a classic example where they have these intuitions,
Mm.
but they're just not evidenced, and so they end up looking a bit silly
Yeah,
because they fail to acknowledge any theoretical limitations in a lot of them. For example, the accuracy. Um, Explanations will be accurate if the training data explanations are accurate. No, they will be accurate if your model is accurate. Is a big statement that they're missing there. And I think one of the things, I don't know, that we might want to pay attention to and learn from this is, if we have these intuitions, they're better incorporated into this sort of evaluation section where we can go through each one and justify them. That lends a certain strength to the way we were thinking of doing things in our evaluation for the case representation paper, when we were talking about how do we justify each point. Well, we would look quite silly if we didn't, because these guys look quite silly for basically just giving subjective opinion here.
Yeah, definitely, I agree. And things like this is not a this shouldn't be a like a like can be a careless mistake, because I think the one of the basic principles of machine learning or a parametric model basically is that you can't get 100% accuracy ever. There's something called I think Chamat knows this word. I don't remember it now. So where you can't, it's an approximate model. You can't capture all possible combinations. So you end up with this uncertainty where you end up with 99% accuracy.
Yeah.
So
Well, you're modeling a problem, and by its very definition, a model will not be identical.
yeah,
So yeah, you're going to end up in this situation. It's just, I think the real benefit for accuracy with this method is suddenly accuracy becomes a valuable evaluation metric to tell you how good your system is at providing explanations.
yeah, I think that's what they're going to talk about in evaluation.
Yeah.
There are two questions: how useful the explanations, which they rephrase into how accurate the explanation prediction is, which again I didn't agree on, but you know. Yeah.
It's, yeah, it's a shame.
I think the whole idea is that they put this discussion section inside the method, is that because they can't back up most of them
Yeah.
if they presented it as a discussion section.
Yeah, I agree. I agree. I think that they are. I think that they are largely unsupported, and So you're right, Angie. That's why it's here.
Mm.
And I think it just means that we should pay attention to how we do these things
Mm.
going forward.
Yeah, I think the takeaway from this is what I thought is yes, trying to label the data is a really good exercise, but other than that, not really.
Well, I think that also there are limitations to their advantages that they don't acknowledge. So this educates a consumer and may reduce bias, but it's coming with the overhead of an expert look over all your data.
Yeah,
We
they,
know that
which they
if we were
talk
to take,
about.
sorry.
They talk about the overhead a bit
Mhm.
at the end of the paper, but they have completely ignored all the challenges or all the normal characteristics we know of a supervised learning problem, which Nirmali pointed out as well. You don't have a balanced data set at the end of the Cartesian product. You don't really achieve 100% accuracy. Like from a technical perspective, they're not looking at it correctly, I think.
Yeah. And from a structural one, it's very weird to see this advantages section in a paper without seeing a corresponding limitations,
Yeah.
because I think it gives a slightly shinier view than is actual reality.
Definitely, yes.
Yeah, let's maybe move to the evaluations, and then we can talk about, the argue the point they make that it is generalizable. I think that is one of the weakest statements. Yeah,
Yeah.
let's.
So in the evaluation, they focus on these two questions: how useful are the explanations provided by the TED approach? So basically, um, they use the word useful, and how they interpret is, or how they evaluate is, how can the model accurately predict the explanations. So this is a little disconnected, I would say. So instead of evaluating the usefulness, they evaluate whether the model can actually accurately predict explanations, which are two completely different things. But I can see how difficult it is to give a quantitative measure of usefulness. So yeah. And the second one they're looking at is how the prediction accuracy is impacted by incorporating these explanations. Um, Whether the prediction accuracy or the Y label prediction accuracy is it affected negatively by increasing the number of classes, the everything we discussed here with not having enough data for some of the classes, things like that. Um, my problem with the evaluation is it's very two simple data sets, and I don't think they actually address these questions comprehensively enough for us to really take away anything from them. The two use cases they are looking at is tic-tac-toe and this again the loan application, loan prepayment scenario. I'll so what they have done is to annotate, they come up with these rules for the tic-tac-toe scenario. So you have 9 options to select from when you play tic-tac-toe, and they define the features as to where everyone is at the moment and who's playing, and then your next move as Y label and why you made that move. So why you made that move is based on these 4 rules. So you end up with 9 options and 4 rules, which is you end up with 36 outputs in your Cartesian product. So they train on a simple neural network and they achieve for tic-tac-toe. If you didn't have E, the explanation, so you are doing a 9 class classifier, you get 96.5% accuracy. If you had annotated and you perform 36 class classification, the Y accuracy, they say it's improved. And then you have independently the accuracy for predicting E, which is the decomposed of Y and E, which is 96.3% accurate. Um, Again, Well, let's see. So in the next one, what they do is they set set of rules for the loan repayment scenario, where you have set of features and their class label is indicating whether they are how well they performed with repayments once a loan is given in the last 2 years. They come up with a set of rules to say whether they were good repairs or not very good repairs. With that, they come up with 2 good classes. That means you have a good class and 2 explanations, so you end up with 2 good classes in the Cartesian product, and 6 classes where you find some reason why they were not good pairs. Again, they use a random forest classifier for this, and end up with a slightly improved accuracy for when predicting y as a 8-class classification problem instead of a 2-class classification problem. I don't think this is significant. And then you have they show a good accuracy when they predict E, that is decomposed from the Cartesian prediction model. So I don't think these 2 use cases cover to make the argument that the prediction accuracy is not impacted by the introduced increased number of Y labels, and also whether the explanations are useful. But the accuracy seems to be good with respect to predicting the E labels. But again, these labels are quite simple compared to some of the tasks we've seen in the real world. So I'll briefly touch on the other paper where they have a better use cases. So I'll finish this one off quickly. So they talk about several instantiations they would see as alternatives to this Cartesian product, which is multitask setting using the distance loss, which they talk about in the other paper from the same authors. And they talk about how this increases the number of classes, and they say, although we did not observe an effect to stress the algorithm, again, a bit of a stretch from the 2 simple use cases they have selected. And then they talk about the inconsistencies they would see in the explanation. So if we got some experts to annotate the explanations, they would annotate something like insufficient salary using different terminology, salary too low, which should point to the same E, but it could not be. So this can be a challenge when we actually do the annotating process, which can simply be solved by having a predefined list where they go and select. So I don't think that's a big issue compared to other issues we've already seen. And then they talk about how annotating the full data set is not realistic. They talk about active learning, where we ask the user to give an explanation during deployment, could be a useful solution to this, or doing a few shot learning even, where we annotate only set a few prototypical data instances and use that to learn a few shot learner. So yeah, they have talked about these challenges a little, but there are more pressing challenges with supervised learning when we do this, I think, that need to be addressed. So if there's no questions, we'll move quickly to the other one. Here they basically talk about how they instantiated this multitask learning approach, where they learn the multitask learner or the embedding for the multitask learner in a way which we are familiar with, I thought, with something very similar to the metric learning losses. So I think it'll be more interesting here. So what they propose is to learn feature embedding guided by labels and explanations in a multitask setting. I will quickly go here. So in their method, this is what we are familiar with. Instead of having x and y and trying to predict y from x in our method, now we have x, y, and e. And we are trying to predict y and e given x, where we first predict y given x and then e given x and y. So this is just the formalization. And what they use as baselines in this method is, before going into introducing the method itself, they use this regression or classification, depending on the scenario, networks to predict y from x, and also a similar network to predict e from x. So you have two networks separately that predict y from x and e from x, which can be a very good baseline in any case if we have this annotated data set. Now going into explaining their approach, what they propose to do is to learn a parametric model which will help us take an embedding in the future. For example, if it's like a two-layer neural network with a output layer with the number of classes, you take the last layer of the embedding of the two layers and use it as a representation for any input. So what we do is we train a parametric model to predict y and e, or just y or just e, just to train this embedding layer. And how they train the embedding layer is the interesting part. And what we do after we train is they use a k-nearest neighbor approach. This is why they mentioned they have inspirations from case-based reasoning as well. They take the input x, they take the embedding for x, and then do a nearest neighbor search to find the nearest y and e for that text when you are given a new x. So everything depends on learning this embedding, where the predicted or the embedding taken for a new x instance will put it in a space where it's closest to the most similar x's with the y, so that we can retrieve y and e. This is, I think maybe Kyle can jump in and explain it better. It's about learning this feature space where similar ones are close together. But in this case, the similar ones are not defined by the label only, but also by the explanation.
And
So
Anu has a hand raised.
I do have a question regarding this approach. When we use embeddings to decide what our explanation going to be, how reliable is that? Because that depends on the embeddings are generated by our two fully connected whatever neural network, and if there is a bias there, for example, or if it's not discriminative enough, then what results from it? How is that an explanation that can be anything? That's just
sorry. Yeah, I think we will have a better understanding when we look at the how they train this
okay.
layer. So
Okay.
if we learn them as two separate networks using categorical cross entropy or mean squared error as we would usually, it does not enforce them to be in a feature space where it is desirable to perform KNN later, right? So this is what they come up with. This is why they use a distance-based loss to make sure that the feature space created by these embeddings are in a better position to perform KNN, which is an idea I didn't see they refer to, but this is a idea Kyle has explored extensively with deep metric learning, where they use this what is it called, triplet loss, or this
Contrastive.
yes.
Contrast.
contrastive loss, where we make sure that the embedding, we pay attention to the embedding space and the match between two pairs, two elements of a pair, the similarity between them when we learn these feature embeddings. So they talk about two losses. So in a data point, if we take a data instance X and XA and XB, we have a corresponding YA and a YB the label, and also we have EA and EB. How much time do we have? Okay. And then there are two losses. First, between X and Y with respect to predicting the label. And what they define is these margins. Here the cos FAB refers to you, F refers to the embedding. Here they say, yeah, and the cos refers to the cosine similarity. So you take two embeddings and you compute the similarity between those two. If two labels are close together, if some distance is, the distance between the two labels are less than some distance, let's say C is some distance, all these C's. And this means in a regression problem, they are close together, and in a classification problem, that means that's the same class. Then what we want to do is minimize the distance between them. So maximize the similarity. So what we do is to get the distance, we perform 1 minus similarity, and we try to minimize this. And if the distance between two labels are far apart, which means in regression they are far apart, in classification they are two different classes. In the feature space, we want to maximize the distance between those feature embeddings, or the similarity between those feature embeddings over some margin. So they are far apart, and also they are far apart more than some margin we can define. So this is, I think this is straight out of the stratified loss from the Siamese neural networks, because we have the pair. And
Yeah,
then we have
exactly
yeah.
contrastive loss, like down to detail.
And please free to jump in if I'm not explaining it right.
Nah, Dave, you're
okay. So we had the same loss for similar thing for X and E. So we are trying to predict X, E from X, the explanation from X. And again, if they are in the same class, or we have the same explanations, or they are close by, we are trying to minimize the distance, which is maximizing the similarity. And if they are far apart, the explanations are far apart in this case. They are far apart by some margin. And why this is a multitask setting is because we can add these two losses and backpropagate such that both of these losses are minimized. So which we combine here using some regularizer. And yeah, so that is the basic idea. So you learn a network that learn a feature space or create embeddings where similar labels and explanations are close by. Different labels and different explanations are far apart. So when we are given a new instance X and we create the embedding from this parametric model we just learned, the embedding will place it in a space where it's close by to matching Y's and E's, and far apart from the not matching Y's and E's. So when we perform k-nearest neighbor, we select the most suitable Y and E for this new instance. So in the evaluation, again, there are two questions stay the same. How useful the explanation is, which again, they evaluate by the accuracy of the explanation. Again, don't really agree. And then how the accuracy is impacted by incorporating, the prediction accuracy is impacted by the incorporating this explanation. But in this case, it's not as bad as the Cartesian product, but because you can limit to only the occurrences, the combinations that naturally occur. And they look at two data sets for this evaluation, the olfactory data set, which is trying to predict the human perception of molecules such as intensity and pleasantness. And also they have several, what do you call that, perception, 19 different other perceptions that can be, which they consider as explanations to intensity or pleasantness. So if intensity is the decision they are trying to make, this I got the data set. So those other features such as sweetness, chemical, musky, sour, these features they consider as explanations to the intensity they've given. So if the intensity is 5 in a scale of 0 to 10, that can come from high chemical character and also high acidic character, something like that. So in that data set, they have 20, they have many labels. They select one of the labels as the decision, the rest of them as explanations. The same thing they do to this.
Quick question, Angie. For data sets that maybe don't have that kind of luxury of all those features, can feature weights be considered in the same way?
Feature weights. How do we mean that?
We can talk about it later. I was thinking more from the lime weights, because they would also give that kind of a distribution, like in the picture you were showing. So if someone says class A, then you have a distribution of the weights like on the red side.
Yes, I think the difference here is what you mean is something like this. So how each feature contributed to intensity.
Yeah.
But in this case, the explanation is how a subgrouping, subclasses contributed to a class. So something like a hierarchy of class labeling. So we have things like, remember for, it's like ambulatory activities, sedentary activities. Ambulatory activities can be running, walking, and jogging. So they use running, walking, and jogging as the explanations, and ambulatory activity as the label.
Yeah, so it's almost a different set of features. Yeah.
Yes, a different set of features. Yeah, exactly. So in the skin lesion data set, again, they do kind of similar thing where they have this hierarchy of labeling. They have 3 main labels, melanoma something and benign something. And they have another classification where they have partitioned into 20 groups. So they use these 20 groups as the explanations and the 3 main classes as the decision. And in this case, those, as we can see, the explanations don't overlap with other labels. So a single label, say melanoma, has its own 12 groups, which don't appear on the other 2 classes. So again, this can be a scenario where we want to avoid Cartesian product instantiation, but go for a more multitask learning approach.
And does that mean that the 20 partitions can you use something like clustering to achieve it if you don't actually know the partitions?
I think the idea they have discussed here is getting that partitioning from an expert.
Yes, so what I mean is if you don't have that expert, could you use something like clustering to give us those partitions? We can discuss this later. It's fine. It's something that I was wondering. If we didn't have the expert, how would we do it?
Yeah. Looking at the results, they don't really don't make a good argument for accepting those 2 hypotheses they start with. Yes, they have the Y accuracy improved with learning this pairwise embedding. But in this case, they have only learned the pairwise embedding with the E loss. So they only created a feature space where E's are far apart or close by, does not consider Y. But this is for what is it? The skin lesion data set, where you have the subgroupings or the explanations are not shared across the class labels. So you end up with this problem where if you learn the pairwise Y, the embedding space only using the Y loss, you end up in this problem where you can't really predict this E, because the granularity is not enough, and also these explanations are not shared across labels. So they highlight that problem, which is good, and they find that multitask classification, which is not using the distance-based loss, instead you just use the categorical cross entropy and the regularization in the usual multitask setting is better when predicting the explanation. And in this case also, it was hard to highlight which were better, which were worse. This is the olfactory, the sensing, the smell data set. Here they have ignored the pairwise E and Y model. I'm not sure why. Here they have tried that one where you have the both losses. So you learn the embedding space considering both label Y and E, and they find that the Y, the classification accuracy or the performance on Y, predicting Y is highest when you learn it together.
Why do they not consider that as multitask? The pairwise Y and E?
It is multitask, but with a pairwise loss. So when they say multitask classification here, that is the using the categorical cross entropy loss, where you don't consider creating that feature space.
Right. So you don't have a shared embedding there. So
yes, exactly. But
so
pairwise
it's confusing, the terminology in this table, I think, a little bit.
And also there's a lot of information that are not really making any point. So, and then they present, since this is a regression task, they provide the loss, so we have to focus on the minimum loss. And they find the performance on Y, so predicting Y is best when we learn it as a pairwise loss that they introduced earlier. And with performance on E, they find it's best when it's not good when you use any of those distance-based losses, but best when you are using an embedding from a network that learned to predict Y using just mean squared error. So again, not really making their point as to why using the distance-based loss. But I think it's a neat idea. Yeah, so I think that's more or less that with that paper.